think we can get started. We are excited this week to have Tracy Northup as our IQUIST seminar speaker. Tracy's going to tell us about trapped ion quantum computers. Tracy did her undergraduate at Harvard and her PhD at Caltech with Jeff Kimball, and then went to Innsbruck to do a postdoc with Rainer Blatt and has been there ever since. So thanks, Tracy, for coming to speak. And just to let everyone know, next week we're going to have Alicia Kolar talking about superconducting qubits. So take it away.
So Elizabeth, thank you so much for the introduction and for the really nice invitation. I had some wonderful discussions in the past few hours, and it's great to be here. Even if it's only virtually, it's wonderful to have so many people here. So what I want to start off by saying, actually, is to making sure I can switch my slides. Here we go. Is to congratulate IQUIST on this new Quantum Leap Challenge Institute. It's really exciting to read about it, and I particularly wanted to mention this because I think that themes of these new institute are actually very well aligned with what I want to talk about today. So when I look at the press release online about the institute that's just started or that will start soon, I read about connecting different quantum devices in a network and developing a full stack solution for a distributed computing network and imagining new types of node architectures. And so, yeah, this is very much in line with a lot of the research teams in my group. And it also kind of makes me wonder, well, what can I tell these people that they don't already know? But I think that the key there is really in this last point in talking about different types of node architectures, because the architectures that we work on in my group are specifically about ions in an optical cavity. And so I think that that's certainly a different system than the systems that are being explored right now in Illinois, although I learned today that there's an ion trap system being built up recently. So yeah, I'd like to kind of share with you our perspective on linking together these systems. And I think you can actually get also this kind of perspective from the press release for the new institute as well. So this is, I saw this nice picture from Emily Edwards, kind of envisioning a hybrid network for this Quantum Leap Challenge. And so looking at these different types of systems, you can recognize superconducting qubits, but I also think maybe I see some trapped ions in the beginning. Maybe these could be another system as well. It could be like a neutral atom trap, but to me it looks like a trapped ion system, and maybe that could be something like an ion in a cavity. So those are the kind of systems that we're interested in and that I try to give you a perspective on today. So what I'd like to ask today, and the question that I want to focus on is, can we construct future quantum networks based on trapped ions? And this is focused on a particular system, these trapped ions and experiments that we're going to do with them. But there's a longer term vision towards more hybrid models. So I think when we think about these trapped ion quantum networks, it's not that we're envisioning a future where everyone has converted to trapped ions, but we can think of them as one component of kind of hybrid networks in the future that might include nitrogen vacancy centers or neutral atoms or rare earth ion doped crystals, and where perhaps we can link these together via photons and via techniques such as frequency conversion of light. And so in particular, talking about linking up these trapped ion quantum computers, I want to first ask the question, why would we want to use these quantum networks? What makes them interesting for us? And then I want to focus on the idea of these trapped ions as quantum interfaces, what the state of the art is, what people have done already. And in the third part of my talk, I want to turn to the work that we're doing in Innsbruck and our ongoing efforts to link together two remote ion traps separated by about 400 meters in two different buildings here on our campus, and coupled to optical cavities. And then wrapping up, I want to try to think about how we can scale up this very much proof of principle system. How does this scale to something in the future that we'd like to see built? So to start off, yeah, why are we interested in these quantum networks? And I want to show you kind of a vision or a sketch from a European collaboration. This is part of the so-called EU quantum flagship, And this is one of the teams from that quantum flagship collaboration that I'm a part of. It's called the Quantum Internet Alliance. And there's about 20 odd partners that are working together in this collaboration. This is kind of one of these images from that, an EO-centered image of what a quantum internet could be. And it looks very dramatic and flashy, linking together these different locations across Europe. But, what does this mean? What would it be? What would it mean to have a quantum internet? I think we can break that down into two questions. What would we want a quantum internet to do that our classical internet doesn't already do? And once we can define the goals for a quantum internet, what kind of structure would we have to build to accomplish those goals? And so in addressing those questions, I think something that's an article that I find really helpful is a piece from a couple years ago in Science by a few of my collaborators within this Quantum Internet Alliance, and that's Stephanie Wiener and David Elkus and Ronald Henson, who are at Delft. And this is a nice diagram from this Science article where they, on one hand, consider the different possible stages of a quantum network, and also these different applications. What I like about this diagram here that you see is that it's kind of going from the simplest things on the bottom upwards in functionality to the most complicated thing you could imagine on the top. And so it presents, I think, a useful picture that a quantum internet is not something monolithic, that there could be different kinds of quantum internets. There can be very simple stages that also are good for certain applications. But if we can climb all the way up this ladder, we can do more sophisticated things. So just to highlight a couple of examples from this diagram, at the bottom at this level that's called a trusted repeater would be where you could do what's known as quantum key distribution, the idea that you can establish an encryption key that's provably secure. And certainly Paul Kwiat in Illinois is an expert on this. This, what's amazing about QKD is that this is already a commercialized technology. But you would already have to start climbing up this ladder if you want to go over long distances beyond so-called trusted repeaters. And there you start needing kind of more sophisticated things. You start needing resources like entanglement. And if we go even a few more steps up the ladder, for example, if we had something like a quantum memory, like the things that Virginia Lorenz or Elizabeth Goldschmidt are working on, then you can talk about doing things like blind quantum computing, where you could say, I have some computation I want to do. I have some set of limited resources. Can I send that to a server? In the same way that we're also, we're all the time querying classical servers to do tasks that we can't do on our local computer. But I also don't want that server to know my problem, to understand what the thing is that I'm asking it to solve. And so this is an example of a really nice quantum task you could do with a so-called quantum memory. The last example I want to consider is not all the way at the top. We're not going to be quite that ambitious. We're going to imagine that we only have a few qubit fault tolerant computer. So we have a quantum computer, but maybe by itself, it doesn't let us solve problems that we can't already solve. And so that would be the difference between few qubit fault tolerance and maybe going all the way to this the top of this ladder, where you have some kind of a quantum computer that lets you solve otherwise intractable problems. But if we had a computer that on its own wasn't good enough to be too interesting, still we might be able to solve interesting problems by linking together these computers. And so this is kind of to emphasize that quantum networks or a quantum internet can be a really interesting concept, not only for quantum communication, but also from a standpoint of quantum computing. So I want to give some examples, and in particular, the trapped ions that I'm going to talk about today are really one of the leading platforms for quantum computing. I'll tell you a little bit more about the ions later on. I just wanted to show you a shiny picture of them to start out with. So this is from Rainer Blatt's group in Innsbruck, where it's just a picture of a vacuum chamber, and inside kind of glowing is this ion trap. So, what are people doing right now? Well, here's an example of two papers, both from Innsbruck, from Rainer Blatt's group, and from Chris Monroe's group in Maryland, where people can work with, do computations, in one case with 20 ions, another case with 53 ions. The first case is an example where you can do gate operations, quantum gate operations on individual ions. And so sort of even though these papers are a couple years old, there's been more development since then. About 20 is kind of the idea for having complete control over each ion in that register. And if you only want to do, say, collective gate operations, then you could talk about, maybe kind of 50 or 60 ions that people are doing experiments with these days, or even 100 ions. So you can certainly do a lot of interesting things, and there's many people who are thinking about how to use those systems to address problems that we can't solve classically. But certainly, we're also interested in going beyond tens of ions, and there are many quantum problems where we would need not only hundreds, but thousands, or tens of thousands, hundreds of thousands of quantum bits in order to achieve this, the kind of quantum computing goals, things like factorization of numbers that we can't do classically. So what would it mean to stuff more ions into these ion traps? In practice, it means that you take more time for quantum gate operations, so it slows everything down, and it gets noisier because you have crosstalk between the couplings between these ions. So things get messier as you start to add more ions, and people have known that for a long time. So back in 2002, Dave Wineland's group suggested a so-called quantum CCD architecture, where you could build a kind of an ion trap chip that would allow you to shuttle ions around into different zones. And that would be, that's understood in our community as an approach of how you could increase the ion trap number, maybe to some hundreds of ions. Here's a recent example of this kind of shuttling from Ferdinand Schmidt-Kahler's group in Germany. And I think there's also been a really nice recent paper out of Honeywell showing this kind of quantum CCD architecture implemented in putting together a lot of the different pieces in one trap. But as I tried to suggest, this can kind of get you up to maybe several hundred ions. But what if you want to talk about thousands or even millions of quantum bits? It would be hard to imagine having all of those on a single chip in a single vacuum chamber. Again, this is something that people in the quantum information community have been thinking about for a while. And this is a nice diagram from Chris Monroe and Jung-Sun Kim from a science paper a couple years ago. And you can see here what the concept is that they're sketching out is an ion trap where they're trapping two different species of ions conceptually, and then they're coupling information from the ions into optical fibers. And so what you should imagine is that this ion trap is not just by itself, that there are other ion traps out there in the ether that, that are linked via these fibers. And so this is a way that these ions that we see here, where there's only about 20 of them, can talk to many, many other ions. And you can then distribute the challenge of trapping. Here's another sketch of the same concept or a similar concept, where you can see ions that are coupled, in this case, again, to light, and this idea that they're kind of being shuttled through an optical, in this case, it's an optical cavity that's allowing them to make links with distant ions. So in this picture, you sort of see the explicit concept of linking together ions in different places. So this is all to say that what I want to kind of put in your head is the idea of making optical interconnects can allow us to scale up ion traps beyond a single device, and may in the future allow us to solve computing problems that we can't address otherwise with a single device. So hopefully, that's an exciting enough reason to start looking at linking together these systems. And so now I want to tell you, where are we now with these trapped ions, and kind of going back a couple of steps, what is this shiny vacuum chamber doing? What's going on in there? So this is just the picture I threw up to start with. But what we actually have inside of that vacuum chamber is, it's quite simple actually. It's just a couple of electrodes, and we ground two of them, and we apply radio frequency voltage to the other two. And that gives us a so-called pseudo potential in 2 dimensions. And then by applying DC voltages in the 3rd dimension, we essentially get a potential well for an ion, a charged particle, in 3 dimensions. So this is known as a linear Paul trap. It provides a confining potential for charged particles in 3 dimensions. And then once we have those particles trapped, we can coherently manipulate them And we manipulate not only the electronic degree of freedom of the ion, but also the motion of the ion. And typically that's done either with lasers or with some combination of lasers and microwaves. What I'll tell you about today will only be with lasers. It kind of depends on the ion species when you might want to use microwaves. So this is just a cartoon of an ion kind of happily rolling around in a potential well. And you should think of that kind of multiplied by 3. We can decouple the 3 axes of an ion trap and think of it as trapped in the X, Y, and Z dimensions and just kind of rolling around in this nice potential. Ion traps are really deep. So it's about 10 electron volts deep. Think about that as compared to, room temperature is 1/40 of an electron volt. Visible light is like 2 electron volts. So this is way deeper than room temperature. Those ions are kind of only going to leave the trap if they have a really high energy collision, or often if there's some chemistry that happens with hydrogen or water that's in the trap. So people are trapping ions that then stay in these traps for days or even longer, weeks sometimes. And also, the trap frequencies, the frequency at which you should think about the ion as rolling around in that trap is at about megahertz trap frequencies. The radio frequencies that we apply to these electrodes are kind of maybe 20 or 30 megahertz. But the trap frequencies are just the rolling around for the ion about a couple megahertz. Here's a very pretty picture. Again, from Rainer Blatt's group. So in my own work, in my group, we're kind of working with 1 or 2 ions. But this is really a nice ion crystal of some 50 odd ions. And you should think about these ions as separated by about 5 microns. And what we're looking at here is the fluorescence. So we're illuminating them with lasers and collecting all of the photons that are getting emitted from this excited states that are continuously being re-excited. So we're collecting the light, we're making a pretty picture on a camera. And they're repelling each other because they're all charged. So this is the Coulomb interaction that you see pushing the ions apart from each other. But at the same time, the potential well that I sketched out earlier is pushing them back together. So the reason they form this long string is this competition between the global potential and their Coulomb interactions. Here are some fun videos of the collective, or camera images of the collective motion of the ions. So you can see that they have different, just like coupled harmonic oscillators that you saw as an undergrad, these ions have collective motional modes, either the center of mass mode that you see on the left, or this mode where they're kind of oscillating out and back together. So those are kind of simple pictures of trapped ions. I'm not going to describe in detail how one does or gate operations between ions, but the key is to know that you can do quantum gate operations by relying on these shared motional modes. I want to now come back to this picture of this different kind of functionality for networks. And what I want to point out here is that all of the things at the top of this kind of chart of a stage of quantum networks, these are all kind of local network properties. So a quantum memory is not something that's necessarily distributed across a network. A quantum memory is something you have at a single node of a network. Or a quantum computer, whether it's just a few qubit fault tolerant or really a super fancy quantum computer with many, many qubits, that's something you have at a single node. And these are the kind of things that actually quantum ion traps have really excelled at in the past couple of decades. So ions as quantum memories have shown extremely long coherence times. So what we're asking here is, I have a quantum state, and how long can I store it undisturbed from the environment? This is a result from a couple of years ago from Kyewon Kim's group, and actually recently his group has shown more than something like an hour for the same ytterbium ions. So you can store information for many, many minutes undisturbed in these ions. And it's not just that you can store information, that you can use those memories, but you can also manipulate that information and use these ion traps as computers. So these gate operations have some errors, and ion traps have extremely low error rates. So when you want to do gate operations involving just a single ion, the error rates can be as low as 1 part in a million. And gate operations involving 2 ions together, this is something like 1 part in 1,000. And that's really what you would need to build up then a universal set of gate operations for a quantum computer. You would need to combine these single qubit and 2 qubit gate operations and just concatenate a bunch of them. So what I'm trying to convince you is that the things at the top of this list of quantum networks, this is where ion traps shine. And finally, here's kind of a picture also of ion trap that's a little bit fancier than the one I've showed you up above, but it actually does the same thing. So this is a chip-based ion trap. It's fabricated, so it's microfabricated. It has a little slot for loading ions. And there's a paper here where they really consider the status quo of ions today and how one could get towards fault tolerance. And there's actually a handful of companies that people have started up recently. So IonQ in Maryland, Honeywell, of course, is a well-established company, but has recently got into the ion trap business. AQT is a startup here in Innsbruck. So people who are really now kind of working to take these ion trap technologies out of the lab and commercialize them for quantum computing. So then what's the story with ions at the bottom of this list of quantum network functionalities? And that's where I want to emphasize that these properties are non-local. These are the properties where we have to think about nodes that are linked together over channels in a quantum network, and where we're going to have to think about distributing quantum properties and protecting fragile quantum states over long distances. And so that's going to be a picture where we can't just solve everything at a single ion trap. We're going to have to link together remote ion traps. And I would say, to make a general statement, that is where ion traps are not as developed. There's not as much research that's been done there about linking together remote ion traps. But still, there's been really a handful of beautiful seminal experiments here. And I want to just kind of outline what has been done in terms of linking together remote traps. So what you should keep in mind is that the state of the art is about linking together two remote traps in the same laboratory, but kind of separated by some meters. And the first group to do this was Chris Monroe's group at the University of Maryland. So in 2004, they entangled ions and photons, and then that let them kind of 2007. So more than 10 years ago, they were the first group to demonstrate this remote ion photon entanglement. And the picture here I'm showing is actually from their 2015 paper, where they made it a lot more efficient. And so I'm just going to kind of describe to you the key concepts of what was done in order to generate entanglement between ions and remote traps. So I've just kind of copied two pictures of an ion trap from their website to give you the idea that they have ion traps in two different locations, and those are in two different vacuum chambers, which you see sketched out here. And then they're again sort of separated by some meters. In one of the ion traps, they have two ions. And what they can do is entangle each ion with a photon via spontaneous decay. So this is a little electronic level diagram of the atomic physics structure here, where you can excite an ion to an excited state. It has two possibilities to decay. And that means that either it decayed to the left and you make a certain kind of photon with one polarization, the sigma plus polarization, or you get to decay to the right and you make another kind of photon with sigma minus polarization. So what you then generate is an entangled state between the electronic state of your ion and the polarization of this single photon that was produced in the decay process. So at this point, you have a photon and you have an ion, they're entangled. And you can see that in both cases, above and below, from the two modules, the photons are collected with a lens, objective, and they're sent over optical fibers to a single beam splitter. And that beam splitter has the task of erasing information about which module the light came from. So if we have then photons after this beam splitter, we don't know whether they came from ion trap module A or ion trap module B. And the final step is this detection setup. So we see 3 photomultiplier tubes. They could be avalanche photodiodes. There are various ways that you can have for detecting single photons. And the key aspect here is that this detection event of the 2 photons that were generated in the 2 different modules projects the ions into an entangled state. So what happens is you detect one photon with one polarization, another photon with another polarization, and then you produce 2 entangled atoms, even though they're separated by a few meters and they've never seen each other. So again, first done in 2007 in a really beautiful experiment, improved in 2015. And sort of the state of the art from that 2015 experiment is this fidelity of this ion photon entangled state is 92%. So by fidelity, what we do is we're taking the state that was produced experimentally, the quantum state, and we compare it with a maximally entangled state. In particular, we calculate the projection of that, so we calculate the overlap of that density matrix with the maximally entangled state. Then we learn that this is 92%. And then that allows them to generate an entangled state of 2 ions with a fidelity of 78%. So the numbers kind of, they show that we're clearly in a quantum regime. 50% would be the best you could do here with any kind of classical state. And what's really exciting, I think, about these experiments is that they're able to entangle ions about 5 times a second. And the entanglement or quantum states can kind of stay alive in those ions for about a second. And this experiment was the first time in this 2015 experiment that this remote entanglement was able to be demonstrated faster than the states were decohering. So it was sort of, you can create these remote entangled states faster than they fall apart. And it's kind of maybe intuitively easy to see that that is something that's a prerequisite for scaling up these systems to more complicated networks of entangled states. And then as far as I know, this has been demonstrated in kind of one other system since then, and that's the nitrogen vacancy centers in Ronald Hansen's group at Delft. So it's a very, a very rare achievement to be able to do that experimentally. More recently, just in the past few months, David Lucas's group in Oxford working with strontium ions has kind of pushed up these numbers here. They have higher fidelities. They can generate entanglement faster. Although I think that their coherence times, they're not yet at this level. I think they weren't reported in that paper. So the big picture here is this is a really exciting prospect. There's been a couple of breakthrough experiments that have generated remote entanglement between 2 ions. And at the same time, if we want to be skeptical and think about kind of linking together future systems, we have to admit to ourselves that, entangling things every couple of seconds, or, maybe 100 or 200 entanglements events every second, this is something we're going to have to improve in order to generate much more complex network architectures. So we can ask, are there methods to collect photons more efficiently than with the kind of lens systems that were being used here? And also, are there other ways to generate those photons, not through spontaneous decay like I showed you here, but through coherent processes? So there's certainly an answer to the second question, which I'm going to show you now. The first question I would say is somewhat debatable whether the method I show you now can really increase the efficiency, but that's something that we're trying to find out. So this brings me to the third part of my talk and to our work on coupling these trapped ions to optical cavities. So I'm going to show you a picture now, a photograph from the kind of experiment that's been a workhorse in my group for some years. So we've been using this ion trap, which you'll recognize in the center. It's just kind of rotated 90 degrees from the picture or the schematic that I showed you before of an ion trap. So the center of the picture, we have an ion trap, but then we also have an optical cavity. So what you see here are kind of 2 metal cylinders. And what you have to know is that inside of these metal cylinders are highly reflective mirrors. They're separated by about 2 centimeters. And so this on the upper left-hand corner is like a schematic of the cavity where you can see a standing wave mode of light. It's infrared light at about 800 nanometers, 850 nanometers. And so there's a standing wave mode that can form inside this cavity. And the reason we built the cavity around the ion trap is we want to study the interaction of the standing wave with the ion. And in fact, the interaction at the level of single photons. So I'm going to now kind of step you through the kind of experiments that we're doing here and how we go from just having an ion trap in a vacuum chamber to looking at interactions with photons and ions. So the first thing we need to do is to load the ions in our trap. And that happens with an oven. So what we put into our vacuum system is kind of a tube, like a very narrow metal tube of calcium atoms. We heat up this tube, and that emits kind of a directed beam of neutral calcium atoms. And when we construct the chamber, we build it in such a way, so the tube is actually in the lower left-hand corner, just below the photograph here. And there's a hole in this metal piece that you can't see. So where the yellow beam is cutting through the metal piece, that's actually sort of a hole that the atoms can fly through. And they would fly behind the first blade of the ion trap that you see, but in front of the blade that you can't see. And they would fly into that trapping region. And when they get to that trapping region, they see a bunch of lasers which photoionize the neutral atoms. And as soon as this laser then pulls off an electron, then it sees the ion trap potential from these electrodes, and then it's trapped. And so we can image it on a camera. So here we're looking at ion fluorescence. Actually, before we can image it, we need to cool it down a little bit. We add some additional lasers in order to cool the ion, and we can cool it to the so-called Doppler limit, where it just has about 10 or 20 quanta of motion. So about 10 or 20 phonons of motion for these ions. So here's a kind of a sketch of the lasers that we use to cool down the ions to the ground state. So in this story, I need to tell you about two ground states, or in fact, a ground state and a metastable state of the ion, and an excited state, and that's enough to kind of put the ion in a cold state that we're interested in here. So now we've got a cold ion here. It's fluorescing. We're looking at it on the camera, and so how do we couple it to the optical cavity? How do we show that it has something to do with the light in the cavity? So what I've sketched here is a beam that comes in from the left-hand side, and it's red. So we're going to take a laser, put it into the cavity, and so that's going to form this standing wave. And we're also going to take another beam, and we're going to shine it directly on the ion. And these are the two beams that you see in the right-hand side. These are kind of labeled at 397 nanometers and 866 nanometers, and they correspond to two different transitions of our ion. And so the important thing to know is that you need both of these beams in order for us to see fluorescence from the ion. Because if you only have one, the ion will fall down to the third state, and it will be dark. We won't have any signature of the ion. So we need the ion to interact with both beams, and the ion is only going to interact with both of these beams of light if it can see the standing wave structure of the cavity. So what we can do is we can move the ion through the cavity structure. We do that by tuning the voltages on our electrodes. And so I have a little cartoon here where we translate the ion through the standing wave structure. We change the voltages, and the plot that you see above, this is what we measure when we look at the fluorescence of the ion. So we can clearly see this kind of standing wave intensity, and we can figure out by adjusting the voltages how to put the ion so that it has a maximal coupling to this optical cavity. And we can do that with two ions. So we can trap two ions and we can translate them together. And here's a picture on the right-hand side of us doing the same thing. And here we can kind of draw little boxes on our camera. So we can collect light only from one ion and from the second ion, and we know which light came from which ion. And we see that they kind of go up and down together. So we see two ions are bright at the same time, two ions are dark at the same time. And that's because they're actually going through neighboring maxima and minima of this cavity. So we can play games where we can position one or two ions, or even more ions actually, in maxima or minima of this standing wave. So we have now an ion in our trap, or two ions. And what we've done is we've chosen how to couple it to the standing wave mode of an optical resonator. And now we want to look at interactions between single ions and single photons. This is where we use a so-called Raman process. And so I'm going to tell you again about these kind of different levels. It's a pretty simple concept to understand. So the picture is, we should think about the ion here on the left-hand side in a ground state. And we're going to use a single laser beam here, which is drawn in blue. And then we have a cavity here, not a laser, but just the cavity itself on the right-hand side. And we tune the cavity length so that the cavity is resonant or near resonant with the transition between the excited ion state, which is labeled P3 halves, and a metastable state, which is labeled D5 halves. So the cavity is tuned slightly off resonant with one transition. The laser is tuned slightly off resonant with another transition between S1 half and P3 halves. And we match the frequencies of this laser and the cavity, so the difference between them matches the difference between those two states at the bottom, the S and the D state. And what that does effectively is it lets us transfer the ion from the left hand to the right hand side. And it should allow us to avoid spontaneous emission from the excited state. So we should just move the atom from the left to the right. We should generate a single photon, but this is what's known as a coherent process. It can be described by the unitary evolution of a Hamiltonian, and we should also be able to run it backwards. because we generate a photon in the cavity, but we could also reabsorb the photon, map it over to the left-hand side. That's good as long as the photon is in the cavity, but at some point it's going to leave. And that's great also, because that's the information that we want to take out of the cavity and potentially send somewhere else. We can also tell when we're in the left-hand or the right-hand state on the bottom. And we can do that with so-called fluorescence detection. Those are these images that we were looking at on the camera before. So what we can do is shine in another blue laser that couples to another excited state. This laser is at 397 nanometers. And we see the ion fluorescing if we're in the left-hand state, the S state. But if we're in the right-hand state, the ion doesn't see this laser and it remains dark. So these are kind of the key knobs that we have to turn with this ion. And there's a final knob that's actually very important for us. It turns out that these two states, the S state and the D state, so this is a ground electronic state and a metastable state with a lifetime of about a second. These two states, we can couple them together via a quadrupole transition at 729 nanometers. For the experts, you can use a titanium sapphire laser that's stabilized to about a hertz. So we can coherently transfer a population on the ion between these two levels. So now we have all the tools that we need to play with this atom and the photon. And something that we did some years ago was to entangle ions and photons. So I'm going to quickly show you how you do that. But so the key message I want to give to you is that this is an alternate method to the spontaneous emission I showed you before. So one way to entangle ions and photons is to put the ion in an excited state where it has two different channels to decay. That also works for atoms. It also works for various different kinds of quantum emitters. Another way to do it is the kind of coherent process I'm going to tell you, where you give it two different paths to coherently evolve. So I've shown you one path where we go from S to D and we make a photon. But it turns out, okay, this D manifold here, this energy level for the ion, it actually has 6 different Zeeman states that we can split out when we apply a magnetic field. So we have access to multiple different levels. So what we do is we drive 2 parallel processes, both of which generate photons, and we can choose our transitions so that those 2 photons are polarized in orthogonal directions. So basically, what we do is we apply 2 different laser fields to the ion, and one laser field generates a horizontally polarized photon and puts the ion in the state that I've labeled D. And the other laser field generates a vertically polarized photon and puts the ion into the other state. And then what we do is we turn on these 2 processes at the same time, and they balance each other out. And so either we're in the state D with a horizontally polarized photon or the state B with a vertically polarized photon. So it's analogous to the decay process I showed you before, except the difference is that this is something that you could run backwards and forwards again, ideally. That's the theory. What you can do is what's known as quantum state tomography to kind of make a whole map of the system and understand the joint state of the ion and the photon and how you can describe them together. And then again, you can compare the state that you generated in the lab that's labeled with rho here, the density matrix for the whole ion photon state. You can compare it with the state you wanted to generate, and you can find that you're very close to the perfect state that you were trying to achieve. And then what we also could do is play with the relative phase of the 2 laser beams that we use to generate the state. And that allows us to prove that we can generate various different kinds of target states. I mean, I would argue that that's a particular strength of using this coherent approach, this kind of cavity-mediated interface between light and matter versus an approach based on spontaneous emission, is you have a lot more control over the particular entangled state that you generate. So I have a handful of lists here about what the advantages of this kind of cavity-coupled system are for quantum networks. It allows you, as I just mentioned, to tune both the amplitude and the phase of your entangled state. It also allows you to tune the temporal wave packet of the photon that you generate. I was discussing actually with Virginia earlier about kind of the interesting ideas for tuning wave packets and how this can be useful for quantum memories. Here's a picture as a function of the time when we detect a photon. Here's kind of what these photons look like coming out of our cavity. So it's the histogram, it's the probability to generate a photon in a particular time bin. And what you can see is that these photons are very long in time and also in space. These are kind of microsecond long photons. And by tuning the field that generates them, we can play around with the shape of the photons. we can generate them in a very well-defined mode with near unit efficiency. And that's the difference between kind of in free space, a spontaneous decay picture, where the photon can go off in any direction. And the idea is that you put a lens as close as possible to try to collect as much light as you can, but really it can go anywhere. Here it's generated in a well-defined mode. And there's also no trade-off between the collection and the efficiency, the collection efficiency and the quantum state fidelity. So as a final note, what I want to show is something that we subsequently did is to use this ion photon entanglement to entangle two ions in the same cavity. In this case, each ion was entangled with the photons left. So this is very analogous to the earlier experiments I showed you about entangling distant ions. At the time, we only had a single cavity, so that's what we did. We put them in the same cavity, and we were able to show that we could generate through what's called a parity measurement, looking at fluorescence again of the ions and comparing different phases of the rotations that we would do on the ions of gate operations. We were able to show that the fidelity of this ion-ion entangled state was above 92%. So this is all what I've showed you is kind of the toolbox of techniques we have for an ion in a single cavity. And what we've been working on for some years now is linking together two different cavities. So my labs, and this is the pictures that I showed you before, are at the University of Innsbruck. So here you can see the picture. So right now I'm on the 4th floor of this building that you see here with the telescope on top, and I'm looking at the same mountains that you see in the picture out my window. And about 400 meters away, there's another building called the Institute of Quantum Optics and Quantum Information. And Ben Lanyon is leading a group in that building that has recently built up a new cavity coupled system. So you can see here, the ion trap is coated in gold. It's a bit shinier, and but it's also otherwise very similar. The cavity is still the same length, 2 centimeters apart, and it couples to the ions in the same way. So in both systems, we can entangle ions with photons. And the question now is, can we do the same thing that was done in free space in Maryland, in Oxford? Can we now generate entanglement here over a long distance? So it's the same idea, right? We want to take a photon from the left, a photon from the right, send them to a beam splitter, erase information about where that photon came from, and then some detection event is going to entangle the two ions. So we have not done this yet. We hope to do it very soon. And what we've been doing so far is, so we've kind of established a first connection between these systems. And what we want to prove is that we really can't tell the difference between the two photons spectrally and temporally, because that's what you need in order to erase information about the photons at this beam splitter. So we do what's called a Hong-Ou-Mandel measurement. And this relies on the fact that if the photons are really indistinguishable, if it's really not possible to tell a photon apart that's produced in my laboratory from one that's produced over in the Akoki laboratory, then they should always stick together at the output of a beam splitter. This is called bunching. This is really beautiful quantum optics, and it's actually not that hard to understand. So if you haven't seen it before, I encourage you to go through the steps. And what it means is that what you see here on the right-hand side, when we send photons that are orthogonally polarized, so we choose our photon here on the left side to have a different polarization from the one on the right side, then that we plot the coincidence probability here in green, and in the middle at time 0, when the photons arrive at the same time, there's a high probability for those photons to arrive at different outputs together. But in the blue case, where the photons are identically polarized, we never detect them at the same output of the, we never detect them at opposite outputs of this beam splitter because they're bunching. And so this is really a nice sign here. This was for us the first sign that these photons are really indistinguishable. And these were the first experiments that we've kind of done in this winter, where we could really link together the labs from the first time, sending photons from the two different systems to an intermediate location to these detectors. We're working hard with Nicolas Angoire's group. So Nicolas is a theorist in Basel, who's working on doing simulations of the systems to understand is this what we expect? So that they look pretty good right now. And we're trying to use his simulations to figure out really what the right parameters are for us to use to make our photons, or to maximize this indistinguishability. We've also been working very hard to sort of synchronize both the timing and the frequencies across our two systems. And we're really hoping that, yeah, very soon we should be able actually to try to make entangled photons. So this was a case where we were only sending a certain polarization. And to make entangled ions, we'll generate ion photon entanglement on the left, ion photon entanglement on the right, and then the measurement of the two photons should project the ions into an entangled state. And the demonstration would be to measure the ions and to generate the density matrix, this quantum state tomography of the two ions, which would allow us to prove that they're entangled. So we're kind of very excited about the next few months. It's also really exciting to, for us in that sense, to have been able to go back into the lab this summer and start ramping things up. And so with that, I want to just take a couple of minutes to look forward and say, where can we go beyond these two node experiments? In my own lab, we're interested in kind of adding more nodes. So how do we go from two nodes to this kind of ambitious vision of a continent spanning quantum internet? We even see a little line there going over to North America. So I've tried to argue a bit more modestly that cavities are really an efficient, tunable, and high fidelity interface between single ions and single photons. And so if we can get these working with, with kind of high efficiency, with high fidelities, maybe this will let us connect not just the two nodes that have currently represent the state of the art, but also to something more complex. However, we're really going to need to move beyond these kind of hand-built laboratory demonstrations. We'll have to be using something that's more integrated and scalable if we want to add serious complexity. So, how can we be more integrated and scalable? We're also going to need to go to build interfaces to other matter-based qubits. This is something I mentioned early on in the talk. A route to that would be to convert the frequencies of the photons that are coming out of these cavities to telecom wavelength. And that would enable us, first of all, to send photons over much longer distances, but also we can talk about then efforts that other people are taking with their favorite qubits to convert photons to telecom as well. So Ben Lanyon, his team I mentioned at Ikoki, they've really been focusing on these frequency conversion efforts. Also, of course, looking even further forward, you're going to want to kind of encode information, not just in a single ion, but in order to protect that information, to correct for errors, you're going to want to encode a single logical qubit across multiple ions. And at that point, you're going to want to think about sort of proof of principle network protocols. So let's start simple though. Let's start to go think about 2 and then 3. And so something that we've been working on in my group is the little experiment that you see in the upper right-hand corner. So I showed you the 2 experiments on the left and lower right before, the kind of workhorse in my group on the left and Ben Lanyon's new experiment on the right. And in the upper right, what you see is a new ion trap. And it's a bit hard to see in that photo. So here I'm going to show you kind of a schematic of it. It's based on a really beautiful ion trap at NIST, at the Ion Storage Group in Boulder, that's called the wheel trap, and that they're using it actually for aluminum clock experiments. And when we saw it, when we heard about it, we realized that we could really adapt it for these kind of cavity experiments. So they're not using it for cavities, but we've now adapted it to include a so-called fiber cavity. So what you see on the left and the right-hand side are little optical fibers, and at the end of each optical fiber is a mirror. So we have now a little tiny miniature cavity, whereas the cavity on the upper left that I told you about before has a separation between the mirrors of 2 centimeters. This fiber cavity has a separation of just about 400 or 500 microns between the mirrors. So we're kind of going down by 2 orders of magnitude here. And the idea is that will let us build a faster interface. And it's also nice that you can kind of put this photon right into optical fiber when you couple it out of the cavity. There's a lot of challenges also associated with building fiber-based ion cavities, and this is actually the 3rd generation of a system that we've been trying to build. So I'm happy to tell you about all of the gory details, but we're excited about the new trap. In the fall of 2019, we trapped the first ions within the fiber mirrors for the first time. This was kind of preliminary data here that we took this winter on coupling an ion to the cavity. Right now, we've been focused very hard on vibration isolation. It's also a particular challenge with fiber-based cavities, and on understanding the role of the dielectrics in the mirrors in heating up the ions. So we've been kind of solving a lot of interesting technical challenges, but I'm optimistic that we can learn some nice things, and that maybe this system would allow us in the future to scale up this bulkier work of art and that we've built above into something that we might be able to reproduce in a much more scalable fashion. I don't know, right? I mean, this is still something that we're learning a lot about. Fiber-based cavities have been used with neutral atoms. They've been used with quantum dots. We're not the first people to couple ions to fiber cavities. This has been done in 2 groups already, in Michael Kohl's group and in Matthias Keller's group. But I think there's no clear solution about how to do it without, while solving challenges about noise and some charging effects. So I think it's an open question, and I think we have a lot to learn in the next few years here. We also have some even more kind of ambitious ideas about integrating a new kind of MEMS-based design that we've proposed in order to translate around these fiber mirrors. So we're going to be starting to try to build up this experiment in the next year or so. And then to wrap up, I want to sort of step back and point out that everything that we've been talking about has been this so-called physical layer of a quantum network stack. So we can think about the classical internet stack, which goes from a physical layer up through a link layer all the way to an application layer. And there are many kind of theorists who have thought about using the same module or the same structure to kind of organize or provide a framework for a quantum internet. So in that sense here, we've been talking about experiments here at the physical layer with ions and about a link layer of generating entanglement between neighboring nodes. But at some point you have to go further up, think about how you would generate entanglement across a larger network, how you would distribute quantum bits here within that network. And finally, you would have to have some interesting protocols that you want to do. And you're going to imagine that in the future, there would be users who, in the same way that we use the classical internet, wouldn't care about everything in this stack. They would only have, some interesting game they wanted to play, problem they wanted to solve, and they would just like to have the answer as soon as possible and as accurately as possible. So again, this is kind of thinking about all of these aspects of a quantum network stack is something that's being worked on within this European collaboration. We've focused on the bottom here. We have ongoing work with Ronald Hansen's group and Stephanie Boehner's group, testing hardware agnostic control software for entanglement, and also thinking with Anders Sorensen and Elm Kashefi about what would be the simplest possible applications to implement here for a full stack demonstration in this kind of so-called quantum network stack model. So with that, I'd like to wrap up, coming back to this question that I asked at the beginning of whether we can construct future quantum networks based on trapped ions. What I hope that I've been able to show you is that this is really a promising direction, that first of all, there's a lot of nice reasons to build a quantum network for quantum communication, but also for distributed computing, that ions have really shown great promise in terms of information processing capabilities and quantum control, that the state of the art is about kind of connecting 2 ion traps at rates of kind of hertz or hundreds of hertz, and that we're hoping to improve upon that state of the art by linking together ion cavity coupled systems. And certainly there's a long list of ideas that people have for how you can scale up these systems. And what we're going to have to see in the next few years is, how practical these are, whether we can actually put these things into practice in the lab. But I think, trying all of them will be a lot of fun. And it's certainly also a lot of fun to discuss really with theorists the big picture about implementing applications and software for a future quantum internet. So with that, let me show you, the people who are now socially distanced, but very happy to be back in the lab here in Innsbruck and working very hard on these experiments. Thank you very much.
Thank you, Tracy, for an excellent talk. You're getting some Zoom applause hands too. So let's see, we've got one question in the chat already. I'll let other people think about their questions. So Ophir asks, how does the cavity line width compare to the free space line width of the emitted photon, and what would be the optimum?
Oh yeah, that's a really good question. Yeah, and I didn't want to overwhelm people with these kind of rates, but so in this case, the cavity that I showed, maybe let me go back to these kind of different pictures of the cavities. So the cavity that I focused on the left-hand side here has a line width of 50 kilohertz, and the spontaneous emission rate to one level of the lambda transition, so to the left-hand side, is about 10 megahertz, and to the right-hand side is about 0.7 megahertz. And then the coupling rate between the ion and the cavity is about 1.4 megahertz. And so I would say, so the problem here is that the spontaneous emission is too high. We would like to make it go away, but there's a lot of other good reasons to use calcium ions, in particular that the wavelength is really well suited for these experiments. So what do you do when you can't turn off the spontaneous emission? We play this game of detuning from the excited state, and that lets us kind of fix the cavity line width. And so the cavity line width stays the same, and then it lets us suppress spontaneous emission, like 1 over the detuning squared, while we suppress the coherent process by 1 over the detuning. So that brings us to a regime where effectively they're all kind of similar, and we can work in a regime where then like the coherent rate, the cavity decay is the fastest, followed by the coherent coupling, followed by the effective spontaneous emission. So this would be the so-called bad cavity regime. And we do have control over it via the detuning. But of course, we would really like to make coherent things better than spontaneous emission. And that's the whole goal with the fiber cavity system. If we can make the coherent process of the ion cavity coupling better by having it happen in a smaller mode volume. So we expect that instead of the kind of, instead of the 1.5 megahertz coupling rate that we have on the left, in the fiber cavity, we would have a coupling rate of something like 20 or 30 megahertz. The line width would be a bit higher, something like 5 megahertz. And then we can also play these kind of detuning games to tune things relative to each other.
So I'm going to ask a follow-up that I had. So how fast do you envision being able to get with this type of system? Because ultimately the photons that you're emitting are, I assume, limited by that cavity line width. And do you think there are potential ways to go even faster than, I think you just said 5 megahertz for the fiber cavity? Because I mean, I guess 5 megahertz is getting up there, but ideally maybe you'd want to be even faster than that.
Right. So from your perspective, with like these, solid state systems, 5 megahertz is really slow, right? And so you could think about having a smaller fiber cavity, but then you're going to run into issues with charges on the dielectrics that are going to make the ions unhappy. So I think, yeah, you're not going to be able to push it so much faster than these kind of megahertz rates. And so I think that's one argument for hybrid networks, where you would use ions for things that ions are good for when you want to do high fidelity manipulation of multiple qubits and error correction. And then the cost would be, even in an optimized node, it's going to be slow. And so if you're going to connect together, if you want to connect together 2 ion traps over a long distance, you wouldn't have intermediate repeater stations of other ions if you don't need that kind of quantum control. You would put your nice rare earth doped systems in there where you would have something multiplexed, where it could be a lot faster, and you could take advantage of temporal and spatial multiplexing and have repeaters that are sort of best at repeating.
Thanks. We've got another question. Can you talk about the details of stabilizing your fiber cavity, and why is the fiber cavity more sensitive to mechanical vibrations and charging than the bulk cavity?
Yeah, thanks. That's a really good question. So in both cases, we're using shear mode piezos that we actively feed back to, and we have another laser in there. So we in this case, it's a laser at 785 nanometers. The ion doesn't see it, so we just put the laser into the cavity. It's invisible to the ion, and we generate an error signal that allows us to actively stabilize the cavity length. And so you can actually see in the upper picture on the upper left, you see these little like, you see some electrodes for these piezo's that are driving the mirrors. And then on the fiber cavity, I think you probably can't see the picture, but the little fibers are mounted on piezo's as well. So I would say that, so the challenge, I think what makes it more challenging with the fibers is that we chose to put the fibers in vacuum on top of in vacuum translation stages. You might know AutoCube as a brand. These are actually from a brand called Smaragd, but it allows us to translate the fibers with respect to each other in vacuum. So that gives us a lot of kind of more experimental control in case things become misaligned, but it does make the whole thing wobblier, right? And those stages have their own natural resonances at about 500 hertz. And so you have to worry about vibrations coupling in from your environment and driving those stages. So that's the vibration story. The charge story is just about the fact that your mirrors are now, your mirror, instead of being a centimeter away from your ion, is now kind of a couple hundred microns away. So any charges on the surface of that dielectric mirror are going to be a lot more visible to the ion than they were on the big mirror.
Thank you. Let's see, I don't see any more questions from anyone, but I have one more really quick. Can you go to your Hong-Ou-Mandel?
Mm-hmm.
Thank you. So you're not phase stabilizing across your two systems, right?
Right, we're not.
But can you talk a little bit about how you're getting the timing and the frequency? I think I see a little tiny bit of beating in your signal, and I was wondering about the width of that Hong-Ou-Mandel dip and whether it matches the width of your photons.
Yeah, so, right, so maybe the quick comment at first would be that there's like schemes based on 2 photons and schemes based on 1 photon. And if you use a 1 photon scheme, you would need to actively stabilize the length. And then that's something, for example, that the quantum dot people do, like Ronald Hansen's group at Delft actively stabilizes and uses 1 photon schemes, which are can be more efficient. But the 2 photon scheme is really nice. No, you don't need active stabilization. So I think we haven't, it may emerge in kind of more careful simulations, but I would say kind of we haven't seen evidence that this would be actual beating or that the simulations would predict beating. So what I think the width that we see here in time does correspond really nicely with what what Nicola's group predicts, and also what we predict from like Monte Carlo simulations based on the photon temporal shapes that we measure individually at the 2 places. Something that I think is the real challenge is basically, or the thing that makes it interesting and complicated, is that the Raman process isn't perfect, and there's a chance for spontaneous emission on both sides. And this is where you lose your distinguishability. And so what we see in our simulations is that if you shape your photons, that is, if you turn on your laser field on the left side and on the right side, instead of just turning it on in a step function, if you gently turn it on, and if you maybe also tune the frequency at the same side, you can kind of have some combination of like Stirrup Raman process that suppresses spontaneous emission, and that's probably gonna make this a bit, gonna improve the dip a bit more.
And then one last question from Paul. Could you use metal coatings on the fiber to reduce dielectric heating?
Yeah, so what we actually have here on the little fibers, what we're using actually right now in the fiber, so this gold thing is actually a coating, a metal coating on the fiber, and the whole thing, or actually no, sorry, the gold is actually a tube now that we put the fiber in here. And so the fibers are actually in tubes, or they're actually sticking out. So they're actually recessed now. You can't really see it well in this picture, but they're recessed inside of tubes. So that should help us. But actually the big difference for us in the new sort of this fiber system here, what you see below here is that the fiber in the lower, and the fiber cavity system, the mirrors are along the ion trap axis. And what you see above is that the mirrors are orthogonal to the ion trap axis. And so what we're hopeful is actually that this orientation of the mirrors along the ion trap axis, we think that that should be really important here, because actually that's where you have DC voltages anyway. So the charges on the fibers in some sense just function as the DC voltage, and you can just adjust the DC voltage plus the charge to have the charge that you wanted to have anyway.
Great.
Yeah, one very quick thing for specialists is that one thing that that's interesting that we've learned is that the next level of dielectric problem might be not the charges, but in fact that the dielectrics themselves lead to heating of the ion, that is kind of, lead to the ion's kind of phonon number to increase. So via kind of like black body emission story. So new problems to solve on the horizon.
Great. Well, thank you so much for a great talk.